The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I'm very grateful to be here today. We have been working, I'll get into this in more detail in the presentation, but we've been working for the last 12 years within DDSB on various updates to our UFC. I wanted to start by just acknowledging the great technical expertise that we benefit from both within the services and then also the AEs. As you can tell from the presentations, Dr. Oswald, Dr. Nato, and others have developed great expertise and have done work that we definitely have benefited from in updating our UFC. So it's certainly a joint effort between the services and DDSB and AE firms. Okay, this is an overview. Okay, when I was thinking about this morning, I wanted to introduce this session, give you an idea of what is this UFC, what do we use it for, how does it differ from other documents that are out there. You know, years ago there weren't many blast design guidance documents, but nowadays there's quite a few that have been developed. So the basic questions I thought that you normally want to answer in such presentations is who, what, where, when, and how. Okay, for us, the who, the where, and the when are defined by the services. They'll tell us who's going to build something, where it's going to be, and when it's going to be built. So that's outside of our purview. But we do have responsibility for defining what we need to design and then how you're going to design it. How are you going to make equivalent protection to whatever you're protecting, personnel, property, what have you. So the first part of the presentation is the what. What is DDSB? What do we do? Why do we have a manual? And then we go through how do we design to meet our requirements. This is where we started. In 1926, there was a major accident at Lake Denmark. It's near Picatinny Arsenal in New Jersey, not too far from New York City. Prior to 1926, explosive safety was handled primarily through application of the American Table of Distances. That was developed by the Institute of Makers of Explosives, which I believe some form of that still exists and the table still exists. But they had gone through various accidents and come up with recommended primarily distances to protect the public from explosive effects. That's what was used. In this accident, there was the realization that, okay, within the installation, you can have lots of different things going on, lots of different explosive operations, and inadequate consideration had been given to one event propagating to another area, going to another area in a fire, and spreading throughout a base and basically taking out the infrastructure as well as injuring a lot of people in the process, killing people in the process. So in this accident, that's what's happened. You have an event start in one part of the base and it carries through the installation and takes out, you can see the picture, it just decimates all the operations there. So I think partly because it was near New York, but also because of the damage, this got a lot of attention. There was a congressional inquiry, and Congress decided to establish the Explosive Safety Board to further safety and prevent a catastrophe like this from occurring again, essentially. So DDSB is founded in 1928, and just imagine if you're the person that is leading this new group. Okay, you're in the 1920s, the knowledge of blast effects is, at least from today's vantage point, very primitive. You know there's overpressure, you know there's fragmentation, and you have some fragmentation data because you're looking at using the weapons and what they do to someone else. So you have some idea of the fragmentation. But as far as really understanding the physics involved, you know, how predicting what would happen, you're not there yet. So what you will find if you go from the 1920s all the way through the 1950s is that the criteria is heavily based on distance, and it still is. Use distance wherever possible to provide protection. Separate things out, have one operation, you know, a required distance away from another, so you provide the protection. You also can use protective construction, but back in that time particularly, there wasn't a very good understanding of what the protective construction was capable of. So that was a kind of a guesswork thing back in that time. So what they did, instead of doing testing because they didn't have the capabilities, a lot of what they did for criteria was just based on looking at accidents and figuring out what kind of damage you had at certain distances and applying appropriate distance requirements. Okay, so let me back up a little, talk more to this slide. DDSP is our focus, and what we do is just geared towards DoD AE, ammunition and explosives. Basically, we provide safety from when the AE is developed through production and all the way through disposal, demilitarization and disposal. So that is our niche. That's what we do. So we're basically on DoD installations, providing the protection to the personnel, to the property, and then also, I'll get to this a little bit later, trying to manage the size of events if we have an accident so they don't get too large. Jumping a little ahead, but nowadays we do have a UFC that allows you to do protective construction design, so that'll be coming up in the next slides. Okay, so the UFC, the purpose of the UFC, there's three things that it is geared towards. It's geared towards protecting personnel. So if you have an operation within a building and you have, or even more so, if you have an operation in one building and another operation in another building, you're protecting the personnel to a certain level between the buildings. You're protecting property. So if you have a very high value missile, you don't want to blast in one bay to destroy the missile in the bay. You want to protect that property. And then we're also trying to control the size of the events. This comes up, we have a lot of production facilities where you'll have maybe 10 bays in a row where you have ammunition and explosives. What you don't want to happen, you hope that if you have a blast in one bay that it doesn't propagate, and you can design for that, so that the explosion in this bay doesn't cause an explosion in the next bay over. What you even more don't want to happen is that those propagate so quickly that the blast waves coalesce, and instead of it being like a 500-pound explosion, it's like 1,000-pound because those two bays added together and made one big boom, or potentially all 10 bays added together and you have a 5,000-pound explosion, and you have the effects from that to the surrounding area. So that is the other area. And it applies, again, to our DOT-titled munitions throughout their life cycle. Okay, the UFC, I'll give you a little bit of history. You know, I talked earlier about use distance. When we had the run-up to World War II, and of course during World War II, there was an explosion of growth in the munitions area. But, you know, there's a lot of facilities, a lot more need, and of course there was a realization in a war effort you can't always provide the distance, but they want to provide some level of protection, if they can. But they don't know what a wall is good for, what you should design for. What happened, and I don't know the exact genesis of this, but it became very standard to use a 12-inch concrete wall to separate explosives between rooms for storage, what have you. It's just a 12-inch concrete wall with number 4 bars at 12 inches each way, each face, and stagger the bars on each face, so the grids are off by 6 inches. And this was used everywhere, basically. You'll find it in a large number of the plants. You have some that use a little bit thicker walls or might have used different reinforcing, but the standard would be the 12-inch substantial dividing walls, which sounds great, except nobody really knew what protection you were getting. They knew they were providing some protection, or thought they were, but they weren't sure how much. During World War II, a lot of this was geared towards protection of assets and preventing one area from propagating to the next bay over, for the war effort. You didn't want to lose all your stuff. But the limits that they had for quantity in a bay were all over the map. And basically, from the research that we've done, somewhere between 15,000 pounds of TNT up to 65,000 pounds. They thought that they would prevent a propagation from one bay to the next bay over. Again, accident data were their key source of reality checks, I guess you could say, and they had accidents and didn't look so good at those higher weights. And so in the 1944-45 time frame, DDSP did some tests. At that time, they didn't understand that a blast environment inside a bay would be different from a blast environment external. So their test was kind of like a Stonehenge test. You have this circle of wall panels, you have a charge in the middle, you set it off, and you see what happens to the walls. Based on that test in 1950, they lowered the limit to 5,000 pounds for non-propagation. Okay, so the 50s go through, and we're getting better on safety, but we still have accidents. And we realize we don't have data for a wide range of explosive weights. In the presentation in 1959 where they talked about this, they said there's a woeful lack of data between 200 pounds and 3,000 pounds as to what's occurring. So, based on that, they set up a working group to look at the effectiveness of these concrete walls. You may wonder, why am I giving you all this background? Well, the reason is that is what led to the TM. That's what led to UFC 33402, was this issue. They did lots of tests. They were surprised by the results. They start around 5,000 and they get a propagation, and then they go to 4,000, they get a propagation. They go to 2,000, they get a propagation. They go to 1,000, they get a propagation. They go to 500, they get a propagation. And they realize that an internal blast intrinsically is different from an external blast, that the load environment is very different, and the risks are much higher than they had thought. And they also, luckily, in the 60s, technology had advanced enough where they could do measurements of the blast environment within the cells. They could start developing design procedures. They had come up with the concept of single degree of freedom modeling, and anyway, the whole science had advanced enough that you could develop a design guide. And so that's the genesis of the manual. Since it came from tests of these SDWs and concepts that followed, it's very heavily geared toward reinforced concrete, thicker walls than the 1 foot even. I mean, that's kind of the minimum in the UFC now, is a 1 foot thick wall. So that was the original 69 version. 1990, it was expanded. It expanded the concrete guidance, but also added guidance for other materials, and I'll get into that in just a moment. Work has continued. We've converted the manual over to a UFC in 2008. Again, there was research testing done that we wanted to implement in the manual from the 1990 publication date. The big thing for us, to be honest, was we had very rigorous diagonal tension requirements, lacing of the rebars. I don't know, for those of you who are familiar with it, it's a very difficult construction technique. And we had lots of defaults of contractors that weren't able to build the things that were designed. And we had research that showed you could use a much more easily constructed system to have that protection. So that was one thing that went into the 2008 version, then other changes as well. More recently, and this is the focus of today, we issued Change 1 in 2014. We have some presentations on that to follow that'll get into the nice, juicy technical details of the changes. And then we unfortunately have Change 2, there was data put in that the equations were wrong, and so Chuck alerted us to that, so we changed it back to what it had been before. What makes our manual unique? Within DoD, a lot of our guidance is limited distribution. And what typically makes it limited is there's munition effects data. If you have munition effects where people can predict injuries and what have you from different rounds, that has to be limited. And we don't have that data, so it has always been an open distribution document. And as a result of that, it's widely used. It's been used for years. It was out since 1969. The procedures are straightforward, so it's accessible to engineers. One of the other big things is, as I've discussed with the SDW test program, we have a heavy focus on internal blast, which makes us unique. Most other user communities are looking at an external blast event, be it anti-terrorism or protective construction design for someone bombing your building or what have you. You're trying to protect the people inside, where ours often are internal blasts. So we have many special requirements related to the internal blast environment. This has been something we've talked about. Back in '69, things were had to be relatively simplistic. There are much more advanced modeling techniques available now. So there's a push in some parts of DoD to go towards that. The problem that we have is we have no control over who designs our facilities. The services let the contracts. They could get somebody that's great, that really knows their stuff, or they could get somebody that just says, hey, I can do blast design, and they've never done it before. And so we have made a decision to try to keep our methods as easy as they can, where you can do there's step-by-step examples you can go through, with the goal of having a safe design at the end of the day. The thing none of us wants is to get a design in and then have to say, you just completely screwed up, you need to start over. So the manual, and for our applications, again, it's a reasonable approach. So what's in the UFC? We have our criteria. There's 6 chapters. It's 1,800 pages. It's a big manual because it has lots of load tables, pressure tables, lots of information in there, so you can do things by hand if you need to. Chapter 1's introduction, and I put this part up because it goes through what we do for personnel protection. We have very specific criteria for what you have to do for personnel, what you have to protect them to. So incident overpressure could be no more than 2.3 psi. They can't be impacted by a hazardous fragment, which is one with a 58 foot-pound energy. That's based on testing back in the 60s of what would take someone out of combat. Not necessarily kill them, but make them where they would no longer be able to fight. And then a thermal flux criteria as well, which is changed to prevent burns. So that's what we do. That's what our criteria largely is. The others aren't used, well, protection category 2 isn't used that often, but we do have that to protect equipment, supplies, explosives. And then our last 2, at least from a designer standpoint, are the same. They're the prevention of a propagation. We are not that refined where we can say that, yeah, it'll propagate, but there'll be enough of a time delay that it won't be simultaneous, that the events won't coalesce. So when we design for 3 or 4, we use the same criteria. So basically, we try to prevent a propagation, not just delay. The rest of the chapters, Chapter 2 gives you the criteria to calculate your blast loads. Thankfully, that's automated. In the old days, you had to do it by hand, and that was not fun. But there's shock and fringe codes that we have available, and we'll be talking later about a Comblast code that updates shock and fringe, where you can calculate that easily. And that's open distribution codes as well. Chapter 3 goes through single degree of freedom systems primarily and how you would use them. Then we got 4 for concrete, 5 for structural steel, which is not as detailed. We don't use structural steel a lot. Main reason being that we usually have a fragmentation hazard, and the steel can't defeat that hazard. So it's fairly limited for us for structural steel. And then 6 is the catch-all for other materials like reinforced masonry, precast, pre-stress, which we have very little, but there are sections, glass, pre-engineered metal buildings, glass doors. It's just a catch-all for whatever other areas we had data. Okay, our working group. We were founded in 2003. As I mentioned, one of the key motivators was the lacing issue with concrete and the difficulties we were facing with construction. But there are also other areas that needed update. So we have representatives from all the services, and we meet annually to go through essentially what is the service need. That's our key driver, and we develop updates and review them, try to keep things moving along. Unfortunately, we don't have that much money, so we have to very carefully prioritize our work. We would love to have money to do testing, but we normally don't, so our updates are based on research that's been done by others. We have benefited quite a bit from the anti-terrorism force protection work. In fact, the masonry updates are based heavily on that, on the work they've done. We try to align requirements where it makes sense. That's something that doesn't always work, but if there is a protection criteria, say for hardened structures and for us that it makes sense, we would use the same criteria. Like we're trying to prevent breach and spall into a bay. It makes sense we'd use the same table, the same figures or prediction equations to do that. Why would we have different criteria if we're doing the same thing? So we use the same criteria where it makes sense. Our manual was developed, as you can imagine, in '69 with English units. There is clearly a push throughout government to go over to metric. We have not done that yet because it would take a huge amount of money to convert everything to metric. So for now, at least, it's still in English units. We want to keep it as an open distribution document. And then correct errors. We have a system through the whole building design guide where if you see a problem with an equation or you don't understand criteria, you can send in a comment. And so we try to correct those. Hopefully that background will let you understand where we are and why we do what we do. This is just a quick summary of the big changes that were done with change 1 in 2014. Major revision to the masonry guidance. For the first time, we allow mechanical couplers, which was a big advance for us. We had it in our manual for many, many years, but you couldn't meet the criteria because you had to have the mechanical coupler take the load without reducing ductility. And the coupler systems usually have some reduction in ductility over the rebar by itself. And so, practically speaking, you couldn't use them. Well, now we have a testing protocol and a way you could allow couplers in some construction. We made some more modest changes, better guidance on what the manual covered and what it did not, expanding the gas pressure curve downward, because we have cases where the weight to volume in a room was lower than the curve covered, giving a little more guidance on lap splice requirements and non-contact laps. And then we did lower our support rotation limit for equipment protection to try to minimize scabbing of the concrete. Future work, we met just this last week. We are in the process of updating the glass guidance. That usually isn't a big priority for us because we can control what people do on the base. But we do have cases where you'll have an operation that's, say, a dock, and they're going to bring in more weight than they had. So previously they were outside the distance arc. They were far enough away that it was okay. They make a larger weight, then now they're inside the arc. So we're going to try to give people guidance on where to go for glass breakage criteria. And that'll basically go to the ATFP criteria so they can do their analyses. We'd like to update our steel guidance. It's based on the 1977 and 1983 AISC codes. So that would be nice to update that. We would like to, this could be a topic in and of itself, but our procedures for calculating gas pressure in a bay are conservative. We'd like to reduce that conservatism, but we don't have test data yet to do it. So we would love to get money to do some testing. Look at codes that we might be able to use to automate the design process. We had a code called CBARCS we used for years for concrete, but it is so old that it no longer runs on the Windows operating system, so we need to do something about that. And then we're talking about this to precast to pre-stress, maybe expand our guidance there, and add new guidance in various areas. I think I'm just about out of time, so let me make conclusions. Okay, our manual is great, but it's for explosive safety. It's written for explosive safety, so you'll have other user communities are like, why don't you have this? Why don't you have multi-story buildings? Why don't you have seismic stuff where we can do seismic interaction with blast? It's not our purpose. We don't have funds for that. It's open distribution, so it's used a lot, and we get referenced a lot in other guides. And like AC Blast Standard references us a lot. So that's a concern for us that it's referenced correctly, but otherwise it's fine. Change 1 has very good changes, the masonry and the couplers in particular, and we need to do more.